Today I want to implement alloc A in my C compiler because currently certain projects like for example raylib or the tiny C compiler compile successfully using my compiler, but then during the linking stage link.exe complains about unresolved external symbol alloc A. And so hopefully, fingers crossed, once we implement alloc A, all of these projects should compile using my C compiler. And so for those of you who might not know, alloc A is a non-standard C function that allows you to allocate memory in a very similar way to malloc. But instead of allocating heap memory, it allocates stack memory. In this little example program here, we first use strlen to get the length of argv sub 0, so like the program name, and then we allocate that many bytes using alloc A. Finally, we memcopy in the program name to test that the alloc A worked. And now a naive way to implement alloc A would be the following. You have your function stack right here, and on it is like the return value, the saved registers, and some locals. So in this case, there would be the length and the stack memory variables on there. And finally, RSP is pointing to the end of the stack. And now what alloc A would do is simply to subtract the length we want to allocate from RSP and return the result from alloc A. Remember that on x86, the stack goes down, so we have to subtract to allocate stack memory. The problem with this simple approach is that when we now call another function, it expects to have space for its argument just before RSP. In this case, memcopy would write its destination, source, and size variables to the space we just allocated using alloc A. To fix this issue, alloc A needs to not just return RSP, but instead return RSP plus the amount of space we need for the arguments. This is where it gets sort of complicated, because this value, the maximum amount of arguments to a function, is only really known at compile time, meaning that alloc A needs to be a compiler intrinsic, meaning a function that is implemented by the compiler. The history of compiler intrinsics in my compiler is somewhat long. There's a lot of residual code from back when I tried to implement a bunch of intrinsics inside of the compiler. But I've realized since then that most intrinsics have an underlying instruction. For example, the under RDTSC intrinsic simply calls the RDTSC or read timestamp counter instruction. And so for these kind of intrinsics, I've implemented a special keyword, the inline wasm keyword, which allows me to just specify whatever assembly should be inlined in the function. But as we have established, alloc A needs to be an intrinsic, so it's time to dust off the old code. So let's get cracking. First of all, I compile the test program using the Microsoft compiler to see exactly what kind of instruction it produces for alloc A. In the assembly, we can see the call to strlen, the results of which are then incremented by 1. Aligned to a 16-byte boundary, because the stack on x86 always needs to be aligned to a 16-byte boundary. Then there are some overflow checks, which for now I'm going to ignore. Finally, the value is subtracted from RSP, and RSP plus 20 hex is returned. Here we said that probably RSP plus the maximum amount of arguments times 8 would be returned, but it aligned that size again to a 16-byte boundary. Alright, it's finally time to start coding. We first need like a global declaration for alloc A, which is always implicitly defined, such that we can call it as an intrinsic. I do this by going to the old intrinsic code in main, and then just allocating a declaration which has the correct type for alloc A, and a token that tells us it is alloc A. I have to manually write out the type of alloc A. So a function returning a void pointer and taking a size argument of size t, aka u64. And I mark this type as intrinsic because in the old intrinsic system, being intrinsic is sort of a property of the function type. Finally, I add this declaration to the global declaration table so one can find it in code. There's actually a mistake here, because my compiler differentiates between declarations and functions. And we push a declaration, but alloc A is supposed to be a function. And so my compiler complained about a redeclaration at a predefined token, which got really confusing. And I was struggling with this a lot. It took me forever to debug, but eventually I finally got there and fixed it up. After that, I started with the age-old tradition of trying to run the thing and see where it crashes. First it crashed on an old breakpoint which was left over from debugging, so I removed that. Then it crashed on a function called checkIntrinsic function call, which was previously designed to allow intrinsics to add some extra checking for arguments. But at this point, the only intrinsic function is alloc_a. So the function is kind of useless for now, and I just if zeroed out the call. Another compile, and we crash in lookup declaration in libraries. We don't want to look up intrinsic, so let's add a case to not do anything for intrinsic functions. And finally, we made it to emit intrinsic. After again if zeroing out the old code and adding a string match for alloc_a, it's time to implement the code for alloc_a. After thoroughly explaining the layout of the stack again in a comment, I first implemented the simple approach. Subtract the size value from RSP and then use an LEA or load effective address instruction to return the resulting RSP plus the size needed for the arguments. As we don't know how many arguments there are until we emitted the whole function, I add a special alloc_a patch list to write in the offset later on. And with that, we can now compile the test program. But upon inspecting the assembly, I noticed that my function epilogue doesn't actually work with alloc_a. I allocate the amount of stack space the function needs in the beginning by subtracting from RSP, and then in the end I just add that space back. But now instead, to work with alloc_a, I have to instead assign RSP to RBP again at the end of the function. And so I did that, and it still seems to work because all the tests still pass, so I assume it's fine. To ensure that the stack pointer is always 16 byte aligned, we first add 15 bytes to the size and then end with not 15 to align it back down. And after making sure the assembly looks good now and fixing up 2 more minor bugs that I encountered, the final step is now to ensure that it also works for a more complicated test case where I use multiple alloc_a's and in between I call a function with lots of arguments. For this, I alter the test program such that it allocates all program arguments, then calls a function with lots of arguments, and in the end makes sure all of the function arguments are still intact. Does that work? No, it doesn't. But after fixing up the test case, it does. And with that, we can now see if it also works on the real-world programs. Raylib now compiles fine, and from what I can tell, works. The tiny C compiler also compiles, but there was one miscompilation bug which I already tracked down that caused it to report some extra warnings. The wasm3 one time was also using alloc_a and now compiles, but I'm not sure it actually works. I didn't test it. And yeah, I hope you enjoyed this video. And if you like the project or would like to reward me for making this video, I would really appreciate a star on github.com/headerlessccompiler. Thanks and goodbye.